let's look at the hyperboloid. See whether you can do any calculation on this. So calculate your, so look at 0.100. So del f is going to be, gradient is 2x, 2y minus 2z. At E1 is going to be 200. So normal is 100, right? And the tangent plane is the YZ plane. What is LP? L for P equal to this, LE1 at V. Right? You have to calculate this derivative of n in the direction of V. So this is P n1, n2, n3. Right? In this case, P is E1, 100. N1, you have to normalize this. So xy minus z, and then you have to divide by something there, 1 over, let's take a unit vector. So V is, the tangent space is now the YZ plane. Okay, so you take V to be 0, V2, V3, right? V is a tangent vector, so V is a vector in the YZ plane. So V is in the form 0, V2, V3. Now, so you can take the unit vector. So norm V is 1, then so V2 square plus V3 square equal to 1. So what is LE1 of V? V is like this. What is of n? No, E1, V is not E1, P is E1, right? Okay. So what is the directional derivative of n? So what is n? You write down n from this. And then of course you have to evaluate at what do you get? So n1 is going to be x divided by this. So and then what you want is, so you are going to have del whatever you have dot v, right? n1 here. So the things that you are going to have in this, okay? But v is now 0, v2, v3. So what do you get here? At the point 1, 0, 0, you have to evaluate this at E1. So which means you can forget the last two coordinates, so only the first will come into the picture. So this is the partial derivative with respect to the first variable dot v. So v, of course, again you will have first coordinate 0 here, so you will get only 2 and 3, second and third coordinates. So what do you get? So you don't have to worry about the first coordinate in this, because the first coordinate, when you take dot product, that's going to vanish. So you just have to look at the second coordinate and the third coordinate of this. The second coordinate of this times v2 plus the third coordinate times v3. That's all you are going to have, right? So what do you get? So something times v2 plus something times v3. What are these? So although the expressions look big, but when you evaluate, everything should simplify, should to a nice thing, I guess. What is under the square root here? Huh? Plus z square. That's all? Okay, so you have to differentiate this one by one, right? N1 is this. So differentiate with respect to x, with respect to y, with respect to z at 1, 0, 0. So at 1, 0, 0 should simplify things, right? So if you n1 therefore is n1 is what? Right. So what is the gradient of this? So we don't have to write down first and then plug in E1. So anganga you can simplify then and there, right? So even here we don't have to worry about the first thing, because that's going to be 0 when you take inner product with this. So you have to only calculate the second thing and third thing here. right? So that means what? For this, you don't have to calculate this because that's going to vanish. So you have to calculate only this and this at E1. So when you want to differentiate respect to y, there is only one differentiation you have to do, right? So x into, so 1 over square root of this is what you have to differentiate. So what we'll get? 1 by this power minus, so you have to differentiate square root of this, 1 by square root of, so x square plus y square plus z square power minus half. Okay, so minus half into this power 3 by 2, right? And then you differentiate this respect to y, so you are going to get 2y. But then you evaluate at 1, 0, 0. So this 2 goes. Y is there. So 0. What about the other one? Huh? That's also going to be 0? There will be z with minus sign or something. No, no minus sign. Yeah, minus sign. Okay. Yeah. So this part is 0, the whole thing, right? What about this? The next one? Huh? The first component is 0. What is the second component? So now we have to, so your n2 is y over this. So again you calculate only the derivative with respect to y and with respect to z. Of course, now there is a difference because there is y in the numerator, right? So 1 over square root of that plus, similar to what we had earlier, y into differentiate this, right? But everything again evaluated at E1. So this will go off, right? This will be 0 because y is there. But this will be 1. When you evaluate, at 1, 0, 0, all these terms will go off, whatever you have here. You have to differentiate something, just like we did earlier. Okay? You will have, again, what, y by square root of that, power 3 by 2 in the denominator, and so on. But when you evaluate at 0, or 1, 0, 0, that will go off. So only this term will give you non-zero, just 1. So what about z? You will have, oh, not this, sorry, n2 itself with respect to z, that's going to be 0, right? So not this term, but only terms of that type there. So what about n3? Minus z. So there will be a minus sign here, right? Something. So again, when you evaluate at 1, 0, 0, so this will be minus 1. No, sorry, now what? This is with respect to y. So with respect to z is what you get, minus 1. This will be 0, I suppose, right? One, this is minus 1. Zero, V2 minus V3. So LE1 of V is going to be 0, V2, sorry, minus V2, V3. Negative of this. So what do you get now? So this is LE1. Okay. So what are the curvatures? So what is the curvature? K1, K2, K. So V3, for example, if you take E3, let's say, take V is equal to E3, then what will you get? V1 is 0, V2 is 0, V3 is 1. So that case you will get 0, 0, 1. So that is LE1 of E3 is E3 itself. What about E2? LE1 of E2 will be minus E2. So minus 1 and 1 are eigenvalues with eigenvectors E2 and E3. So K1 is minus 1, right? The smallest of the two, smaller of the two. So K1 is minus 1, K2 is 1. So the principal directions are minus E2 and E3, okay? Or if you want E2 and E3, doesn't matter. So these are the principal curvatures. So the Gaussian curvature is thus the product of this. So this gives negative curvature at the point E1. When this is at E1, okay. So you should write K at E1, so on, okay, K2 at E1. The curvature varies from point to point. In general, the curvature is a function on the surface, right? Real valued function on the surface. But you can calculate at some other point, say E2 for example, or E3, K, L of E2 and L of E3 you can try to calculate, okay. So calculate what is the normal curvature, that is what is the quadratic form, this second fundamental form, KV at E1, okay. So V dot this, right? So V minus V2 square plus V3 square. So the normal curvature for the second fundamental form. Of course, subject to, when you talk of KV, you restrict to unit vectors, right? So V, norm V is 1, so V2 square plus V3 square equal to 1. So now we can see the maximum of this subject to this constraint, right? Maximum of LVV, but now V is a unit vector, so that will be your K1. The maximum is K2, right? This will be, well, 1 actually. Maximum of this subject to that is 1. Of course, that you obviously see, right? See, these are real numbers. The sum of the squares is 1. So each of them is less than or equal to 1 in absolute value, right? They should lie between minus and 1, both of them. And so what is the maximum when you get, for example, when you take this is 0, this is 1, you are going to get 1 here. When you take this to be 1 and that to be 0, you are going to get minus 1. So that's going to be the minimum value of that. So in the case of ordinary surface, two-dimensional surfaces, you only have two, right? It's two-dimensional, so you only have two principal curvatures. So one is the maximum of this normal curvature, the other is the minimum of the normal curvature. X max KV norm V equal to 1. This is going to be 1, K2 is minimum in this case it is K2 is the maximum, K1 is the minimum. So no, the notational confusion. Right? So the largest one should be called K2, right? So this is K2, this is K1. Yeah, okay, here I have written, it's fine. Okay, the point here is, so at the point E1 that we have calculated, you get a negative curvature, but you are not going to get negative curvature at all points. You may not get negative curvature at all points. That is, the curvature in general may not be a constant. Okay. But we know some cases where it is constant. In the plane, for example, it's constant 0 everywhere. On the sphere, it is constant 1 over r everywhere. Right? These are surfaces of constant curvature. One is constant 0 and there is a positive constant. Right? There are surfaces of constant negative curvature. So the picture there gives you one example. What is called the pseudosphere. So it's got by rotating a suitable curve, which is called the tractrix. This is a tractrix. So if you think of this picture like this vertically, you rotate this like that. So this is how you get. So this is asymptotic to the x-axis here. So the top point is here. So this is going to give you the largest circle there. So this surface is called the pseudosphere. Because this is a familiar shape, right? Although the name may not be familiar, right? Usually the speakers, see, loudspeakers are all of this shape. And what is called the Nagaswaram, the musical instrument, it's the whole thing goes up to some point like this, right? The bottom portion is this, through which the sound comes out, right? And you truncate at some point. That's where you, on the top here, you put something and then blow, right? So narrow this thing, and then you have what is called the Sivali or something, and then blow using that. That's a reed actually, right? Pull or some kind of pull. That's what you play. So that is typically of this shape, right? Speakers and Nagaswaram have this shape. So this surface is a surface of revolution and has constant curvature -1, constant negative curvature. So the pseudosphere is got as a surface of revolution of the curve known as the tractrix. As constant negative curvature. The sphere has constant positive curvature. The pseudosphere has constant negative curvature. And of course, the plane has constant 0 curvature. There are, of course, in general, the curvature is a function of the point. It is not a constant. For example, we'll come to this. We'll see. If you look at the torus, probably I have already mentioned this, but on the torus, you have points of negative curvature, points of positive curvature, and points of 0 curvature. All of them are. So we'll calculate the curvature in the torus. So this surfaces of constant curvature, this positive or negative, Of course, constant zero curvature is comparatively easy to classify. What are the surfaces of constant zero curvature? These are what are called flat surfaces, right? So constant curvature 0 everywhere at all points, right? So examples are the plane, and probably surprisingly, if you at the first look, circular cylinders, but if at first sight it looks not convincing, right? Cylinder has zero curvature, but so if you look at a cylinder, so how do you get the cylinder? So if you just make a cut in the cylinder, it becomes flat, right? It's just a part of the plane. So we'll make this more precise mathematically. Okay, it's locally isometric to the plane. Okay, a cylinder is locally isometric to your plane. So the local isometries are going to preserve curvature. Isometry means what? Distance preserving, length preserving. So if you take a point on the cylinder, there is a neighborhood which you can map isometrically, not just homeomorphically. Homeomorphism doesn't preserve anything except the topological structure. No length preserving anything. So there is a distance preserving map from that neighborhood up to a part of the plane. Okay, so there is a local isometry from the cylinder to the plane. That's why the curvature is 0. So you will see something about isometries sometime today or tomorrow perhaps. Constant positive curvature the sphere. Here also you can give kind of characterization, but in the presence of compactness. Surfaces of constant positive curvature which are compact. Compact surfaces of constant positive curvatures are just spheres. In some way, the spaces of negative curvature are the most interesting and most studied. For example, if you look at what is called the space-time in relativity theory, the four-dimensional space with a suitable Riemannian, pseudo-Riemannian metric and so on. So that has negative curvature. So geometrically and analytically, these manifolds, Riemannian manifolds of negative curvature are most interesting ones, most studied ones. So let's calculate curvatures of more examples. But now we'll go to the other picture of surface parametrization, right? So using parametries, there is a formula for calculating the curvature. I will not prove the formula, just state the formula and calculate some examples using that formula, okay, in the case of two-dimensional surfaces. So the formula itself depends both on the first fundamental form and the second fundamental form. So you have parameterization, which means what? You have maps U to S, right? We are going to look at only the two-dimensional surfaces this way. U is an open set in R2. This lies inside. So these are going to be two surfaces in R3. Okay. So essentially, a parameterized patch is what we are going to look at, right? The surface itself can be covered using these patches. But if you are going to look at only one point, you want to look at the curvature at that point, it's enough if you look at one patch which contains that point. That's what we are going to do. So you have these maps. These are what is called the coordinate map or chart map or something, whatever you want to call it, local chart, right? So phi of uv, let us write. So basically, you are going to look at, when you want to look at a surface, you are going to look at phi of u intersected with S2, your surface. So you can forget about the surface now. So you are going to look at this. So this is again, the notations are classical notations. So we'll use these symbols, okay? Phi uu means what? Del square phi by del uu. I'm calling the coordinates here u and v in R2. These are the mixed partial derivatives. Second partial derivative. So these are the notations used by Gauss himself, I think. So there's continued to be used. And so this involves the first fundamental form. So the other ones, this is universal, but this is, some people use LMN, some people use small e, small f, small g. Doesn't matter. So here the orientation comes into the picture. Okay. So this is, that means the unit normal vector that we have. So you just take dot products with these, right? The coordinate patch phi and the derivatives of n. So phi dot nuu, phi dot nuv, and so on. So phi dot nvv, etc. So these are called L, M, and N. And then the curvature is given by the quotient of these two discriminants that you have. So K is
ln minus m square minus eg minus f square.
So to calculate the curvature, all that you have to do is to calculate all these derivatives, partial derivatives, right? At whatever point you want, evaluate the partial derivatives at that point and take the quotient. So using this, we will try to calculate some of the examples, the torus and other things. Anyway, we will do some more computations, easy calculations.